In this problem, we're looking at 4 separate questions. Let's address them one at a time. Here's the first question being asked. We're asked to compute a nested set of functions. So as usual, we want to compute the inner function first, the inverse sine of radical 3 over 2. That, by definition, means the number between negative pi over 2 and pi over 2 whose sine is radical 3 over 2. That's what inverse sine means. So, using my knowledge of the unit circle, it turns out that this arc will terminate at one of our favorite 16 points. And from some sort of memory, or maybe not total memory, but from some process, however you've conceptualized the unit circle, you should know that this is pi over 3, because the sine of pi over 3 is radical 3 over 2, and pi over 3 is between negative pi over 2 and pi over 2. Again, there's sort of an element of guess and check there, and everybody thinks of the unit circle differently. The point is, however you do that, we now have done the inner function here. We found the value of the inverse sine. Now we can apply the outer function to that. The sine of pi over 3, based on your knowledge of the unit circle, you should know or be able to figure out that that's radical 3 over 2. And while I'm done with this first part of the problem, it's worth noting that in some sense, there was a cancellation of the sine and the inverse sine here. Although it's a dangerous thing to try to say that a function and its inverse will always cancel one another out when being applied in a nested situation like this, or a composition, as it's also called, because there are exceptions to that, and I think the third part of this problem will show an exception to that. But it is sometimes the case that when you apply a function to an inverse function, that they do cancel each other out, and that did happen here. But again, it's worth noting that that doesn't always happen. So you don't ever want to jump to that conclusion just because it happened to work on this particular problem. Let's take a look at the second of 4 problems. Here, we again have nested functions, so I'm going to focus my attention on the inner function first, the inverse tangent of 3. This is the definition of inverse tangent of 3. I'll pause while you read it. And something interesting happened here. I noticed that this arc doesn't terminate at any of our favorite 16 points on the unit circle. There is an arc whose tangent is 3, and it just doesn't terminate at the points that are the most common to us. In fact, the inverse tangent of pi over 3 is not something that I can really simplify without using a calculator and getting a decimal approximation anyways. So it raises an interesting question. If I can't simplify the inner function in this composition or nesting of functions, then how can I proceed to apply the sine to it? Well, it turns out there is a way. And what we want to do is we want to think about the inverse tangent of 3 as some arc that does not terminate at one of our favorite points on the unit circle. And my logic is this: if I can draw a picture of that arc, if I can see it and find where it terminates, I might be able to find the sine of it, because after all, the sine of that arc literally means the y-coordinate of the terminal point. So now my ambition now is to try to get a sense of what this arc might look like. Remember, we're looking for an arc whose tangent is 3. That's the definition of inverse tangent. And because that arc has to be between negative pi over 2 and pi over 2, then it must terminate in quadrant 4 or 1 in general, but in this case quadrant 1, because 3 is a positive number, and the tangent is positive in quadrant 1, whereas it is not in quadrant 4. So I'm going to put my terminal point of my arc here in quadrant 1, and the arc that I'm talking about is this arc right here. Now, if the thought crossed your mind, Mr. Rosilo, how did you know the arc was going to terminate right there exactly at that point? Well, I did draw this to scale, and I'll show you what motivated me to pick that specific point. I picked a point in quadrant 1 so that the ratio of the sine to the cosine, which is the tangent after all, if you can see the colors, that would be the green to pink ratio is 3 to 1. In other words, I specifically picked that point in a place where the y-coordinate would be triple that of the x-coordinate, thus giving it a tangent of 3. As a student, you don't have to do this. In fact, if your drawing didn't look like this, it wouldn't matter, as long as you were just picking some random point to represent this arc, at least in quadrant 1. So don't worry about the scaling and picking the exact point. That's not relevant to the algebra, but I thought I'd explain that anyways. So now I have this image of what my arc looks like. It terminates somewhere in quadrant 1. I don't know exactly where. Remember, my goal is to find the y-coordinate of that terminal point. That's the ultimate goal of this problem. So I thought in so doing, I would label the point x comma y. If I can now solve for y, maybe I'll have to solve for x to get y, but if I can solve for y, I'll have the answer to this problem. So I thought I would build a system of equations. First of all, because the tangent of this arc is 3, then it must be true that sine divided by cosine equals 3, or y divided by x equals 3. So that's one fact that must be true about this point. But remember, this point is on the unit circle, and as such, it must obey this equation as well. So now here's my plan. If I can solve this system of equations, ultimately for y, then I'll have the sine of this arc, which is the sine of the inverse tangent of 3 that I'm looking for. But my immediate goal now is to solve for x and y. So forgetting about the trigonometry, how do we solve this system? Well, I decided to take the first equation and solve it for y, because then I can use the substitution principle by substituting that result into the second equation, and I can now solve this equation for x. Once I do that, I'll be able to then substitute that back in and solve for y. So here goes the algebra. Hit pause if you need more time to process. I'll proceed. Once we get down here, the plus or minus, in this case, that we got from the radical property is actually just a plus. We are in quadrant 1 after all, therefore x is a positive number. Remember, you can distribute that radical to this fraction and get radical 1 over radical 10, which is the same as 1 over radical 10, and I've now solved for x. I could rationalize the denominator, but I won't worry about that now because this is not my final answer. But I have solved for x. And remember, my ultimate goal here was to solve for y, because the y-coordinate is the sine of that arc, which is the sine of the inverse tangent of 3 that I'm looking for. So I thought, well, I'll take this equation from earlier, substitute in the x that I just found, and I now know the value of y that I was looking for. Now I've rationalized the denominator because we don't tend to like radicals in the denominators of our final answer, and I now have the y-coordinate that I was looking for. That's the end of this second problem of 4. Let's move on to the third of 4 problems. One might be tempted here to say that a function and its inverse would cancel each other out, and that the answer would be 11 pi over 6. But as I mentioned during part 1 of this problem, functions and inverse functions don't always cancel one another out. The particular details of when that happens and when it doesn't are very complicated and not worth going into at this point. Your best bet is not to assume that a function will cancel out its inverse, and to just work it out as a composition by starting with the inside function first. So ignoring the inverse cosine, just finding the cosine of 11 pi over 6 can be done by using your basic unit circle knowledge. That should either be in memory or some other mechanism that your brain can do without a calculator. And now that I've got the inner function worked out, I can finish this composition by applying the inverse cosine. Remember, the inverse cosine means this. I'll pause here while you read. And at this point, it's just a matter of guess and check. And we can do guess and check here because radical 3 over 2 is one of those special numbers that corresponds to one or more of our 16 favorite points on the unit circle. So by simply thinking your way around the unit circle and answering this question, you'll eventually come up with pi over 6, because after all, the cosine of pi over 6 is radical 3 over 2, and pi over 6 is between 0 and pi. That completes the third of 4 problems, and this should be a reminder to us that this is a case where the inverse function and the function itself didn't cancel one another out, did they? Here's the last of our 4 parts to this problem. But we're going to follow the order of operations here. Notice there's a subtraction in the middle, and the order of operations would tell us to do the functions before the subtraction, of course. So let's work out each one of these separately. First of all, the inverse sine of 1 means this. I'll pause while you read. And if you think your way around the unit circle, you'll recall that the sine of pi over 2 is 1. For the second function, same thing. We're looking for some arc whose sine is -1, and that would be negative pi over 2. It's a very common mistake for this second function here. You might see it in purple. It's a very common mistake for people to put 3 pi over 2 for this. And while it is true that the sine of 3 pi over 2 is -1, 3 pi over 2, however, does not lie between negative pi over 2 and pi over 2, and thus wouldn't be a valid answer for this second or purple function. Now that I've worked out each of the functions separately, it's simply a matter of doing the algebra, and I'm done with this 4th part of the problem, thus completing all of them.